Here's a map of the world. Can you see this okay? This map of the world has on the horizontal axis population density. And on the vertical axis, we have the energy consumption per person. And I've used logarithmic scales for both of these quantities. The vertical lines show an increase of a factor of 10. Here's the UK with a population density of 250 people per square kilometre and using 125 light bulbs per person. Top left of this diagram is the countries that have very low population densities, 100 times lower, and even higher energy consumptions. Australia, Canada, Iceland using 200, 300, 400 light bulbs per person. Bahrain, top right, has the same energy consumption per capita as Iceland, but its population density is more than 100 times greater. Bangladesh, bottom right, has just the same population density as Bahrain, 1,000 people per square kilometre. But its energy consumption is 100 times smaller, at 3 light bulbs per person. And finally, bottom left, there's no one. But there used to be lots of countries. They're all rushing up and to the right to come and join us in the top right of this diagram over here. Here's Sudan, Brazil, China. Each of these lines behind the country is showing 15 years of progress. From 1990 to 2005, what happened? Population densities went up, energy consumption per capita went up. Now, a nice thing about showing a logarithmic graph is if you take these two quantities, the energy consumption per person, and you multiply by the population density of the region, you get the power consumption per unit area of that region. And lines of constant power per unit area are straight lines on this diagram because we're using logarithmic scales. So this purple line here that connects Saudi Arabia, the world, Jordan, and Bangladesh in 1990, all of those countries have the same power per unit area. They all consume 0.1 watts per square metre. So that's the world average power consumption. Over here is the 1 watt per square metre line, and Britain's a little bit beyond that, consuming 1.25 watts per square metre. America's roughly halfway on a logarithmic scale, so it's consuming about 0.3 watts per square metre. Why is this useful? Well, as I said earlier, renewables also give you power per unit area, most of them, and we can express them in exactly the same units. And we can take this diagram, shrink it down and to the left a little bit to fit on some more lines that I'll add. And here in green are the power per unit area of a few renewables, and I'll add some more to the list in a moment. And wind power, for example, in windy locations in Europe, delivers about 2.5 watts per square metre. Obviously, there are variations around this typical figure. On Scottish mountaintops, you get more, but this is a reasonable summary of the data. And that's twice the power per unit area of the United Kingdom. So now we get an interesting message that if you wanted to match today's power consumption in Britain completely with wind farms, then you would need to have wind farms occupying half the country, or an equal area offshore. Half the area of the country offshore would do the same. On average, the output of those wind farms would equal today's power consumption. Let's next talk about energy crops. Energy crops deliver about half a watt per square metre in European climates. That's less than the power per unit area of the UK. So the message is, if you completely cover all of Britain with energy crops, you still can't match today's consumption. America, on the other hand, is consuming a little bit less, at 0.3 watts per square metre roughly. Therefore, if you covered all of the USA completely with energy crops, you could match today's consumption and have a little bit to spare to allow another 15 years of progress to happen, perhaps. Here's miscanthus, a famous energy crop. And here's some powers per unit area indicating half a watt per square metre being typical of the performance of these European crops. In tropical climates, you can get a bit more, 1 or 1.5 watts per square metre. Let's look at a table of other powers per unit area. So solar photovoltaic panels are popular and still expensive, but hopefully the cost is going to come down. In British climates, they deliver about 20 watts per square metre. Here's real data from 25 square metres of panels on a building in Cambridge. 20 watts per square metre implies that if you cover all south-facing roofs in Britain with solar panels, then you will be able to deliver, on average, 5 kilowatt hours per day per person. So 5 light bulbs on a scale that goes up to 125 for the European total power consumption in all forms. And you might say, that's a bit disappointing. You were hoping a bit more from such a radical action as covering all south-facing roofs. But to get a really exciting contribution comparable to today's consumption, you need to do what the Germans do. Here's a photograph of the traditional Bavarian farming method where you leap off the roof and cover the country with the countryside with photovoltaic panels too. This solar park in Bavaria, notice, does have gaps between the panels where the sun shines through. That's to avoid them shading each other at the extremes of the day. And now the average power per unit area has gone down. The power per unit land area is 5 watts per square metre. So this is twice as good as wind farms. And if you wanted to go for an all-solar policy, which of course would be crazy, but if you wanted to get all power entirely from solar to match today's total power consumption, you would need to cover a quarter of Britain with solar panels rather than half of it with wind farms. Next up, let's talk about tide pools. Tidal pools have existed for centuries, and the latest one in France delivers a power per unit area of 2.7 watts per square metre. And that's very similar to wind farms at 2.5 watts per square metre. So we already know the answer, don't we? If you want a tide pool to make a really big contribution, you want a tide pool not the size of a small estuary, but the size of an entire country. And God, in his wisdom, when he created the British Isles, gave the British exactly such a facility. It's called the North Sea. The North Sea is an enormous natural tide pool in and out of which and round which great sloshes of water pour every 12 hours. So one way of exploiting that natural tide pool is to go and put underwater windmills in places where the currents are big, and they're shown in yellow on this map. And here's an underwater windmill, one of the first prototypes in Britain. These haven't been deployed in farms yet, but we can use back-of-envelope methods to estimate roughly what the power per unit area of those farms is going to be, and it seems plausible in the yellow spots on the map that they could deliver 8 watts per square metre, so 3 times as good as the upstairs wind farms. Therefore, we still need roughly country-sized tidal farms to deliver one of these countries' worth of energy. Hydro facilities in Britain. You multiply rainfall in millimetres per year by the density of water, the height above sea level, and the strength of gravity, and you find the power per unit area of the rain arriving at ground level. And what that comes to is 0.24 watts per square metre, so significantly smaller than the power per unit area of wind farms. So the truth about hydro today in Britain is it's delivering only 0.2 light bulbs per person, and it's hard to imagine it increasing much beyond that. Concentrating solar power in deserts, finally, delivers 15 to 20 watts per square metre. Here are some beautiful concentrating devices with mirrors putting sunlight onto these Stirling engines. And if you pack these at a sensible spacing in a nice desert, you get 20 or 15 watts per square metre. So that's significantly better than the wind farms, but not as much as 10 times better. So we're still in the same sort of ballpark. We still need very large areas occupied by these facilities if you wanted to match one country's consumption. And the same goes, as I said before, for Massachusetts and New Jersey. And something to bear in mind is that Britain, Massachusetts and New Jersey don't have any deserts yet. Some places do. Here's Spain. They have solar facilities here which are being built and which are expected to deliver 10 watts per square metre, so 4 times as good as wind farms. They're based on this prototype from Kramer Junction. Here's another facility in Spain delivering 5 watts per square metre, so just as it's only 2 times as good as the wind farm in terms of power per unit area. Here's a single device, which is a concentrating solar device using very cheap lenses to focus sunlight onto photovoltaics, very expensive gallium arsenide photovoltaics. This one device, which has got a human alongside it for scale, is delivering, on average, 140 kilowatt hours per day. Remember, total power consumption of a European is 125 kilowatt hours per day, and of an American is 250. So this one object here is a rough visualization of what every person needs if you want to match today's consumption from solar. And that's not unimaginable. It's the size of a house, and we each have a house, perhaps. Here's an American president for scale, a former American president, alongside the Stirling dish. One of these dishes delivers, again, a human-sized amount, 160 kilowatt hours per day. Of course, if we could reduce the human consumption, it might be producing 10 people's power. But we need to talk about how to get the consumption down, and we'll come to that in a moment. Okay, so the message of this part of my talk is, if you really want renewables to make a substantial contribution, not just a fig leaf gesture, then the renewable facilities do have to be large. In European terms, they need to be country-sized. In American terms, they need to be state-sized.